Remember where we were. We are solving the Klein-Gordon equation, Klein-Gordon field, in second quantization on curved space-times. For that, we have to solve these equations. The hermiticity conditions on the field and its canonically conjugate momentum field, the canonical commutation, the canonical equations of motion, and these equations of motion, the Heisenberg equations, can also be written in this form. Here is the Klein-Gordon equation. That arises from this here. And that equation gives us the relationship between the canonically conjugate momentum field and the field. Notice that this is rather non-trivial now on curved space-time. In Minkowski space, it used to be simply that pi is phi dot. Now, phi dot is still contained in this, right? Because we have here all the derivatives of phi. It's not an earthquake, but I don't know why this thing is shaking so much. So, so we have all the derivatives of phi, including the time derivative. And if indeed the metric were diagonal, if it was just, you know, the eta metric, let's say, in this case, we would have simply only the time derivative here, and that's what the canonically conjugate momentum field would be. In general, though, it will be more complicated because all of the derivatives can come up in the canonically conjugate momentum field. Now, so the conditions are hermiticity condition, the equations of motion, and also the canonical commutation relations. Now, the canonical commutation relations have to hold on all space-like hypersurfaces. Remember, the canonical commutation relations are equal time commutation relations. And what is equal time in curved space-time is your choice. As long as it's space-like, as long as two events are space-like, there's going to be an observer, could be you, that declares them to be equal time. And we need to have the canonical commutation relations hold on all space-like hypersurfaces. So we must have that the phi's commute with each other, the pi's commute with each other, and the phi and pi have this commutation relation at equal time, whatever equal time might be. So our aim has been to show that the following ansatz for solving the problem completely in arbitrary curved space-times, well, arbitrary hyperbolic, globally hyperbolic space-times, is this. This is the ansatz. The ansatz is that the quantum field can be written as a linear combination of creation and annihilation operators labeled by some value k, which could be momentum vectors, as they would be in Minkowski space, but it could be really just some label. After all, in curved space-times in general, there is no such thing as momentum, because there are no momentum operators. There are no canonical momentum operators in curved space-time. Or to put it differently, Fourier transform is not covariant. If you first Fourier transform and then change coordinate system, or first change coordinate system, then do the Fourier transform, you don't arrive at the same place if you do that. So that is the same thing as saying that there's no canonical momentum, because going to the momentum transform to momentum space is going to the eigenspace of momentum operators, right? No, the only thing that is still left over from momentum space is the sum of the momenta squared, the D'Alembert. That generalizes to a curved space D'Alembert, right? And it's no longer the sum of the momenta squared there. That is the only thing that survives. So in generic curved space-times, the k could be some arbitrary label. Okay, so our ansatz is that the general solution we hope can be written in terms of creation and annihilation operators that have these commutation relations that are supposed to take care and enable the commutation relations of phi and pi, and prefactor functions that are number-valued solutions to the Klein-Gordon equation. They take care of the equation of motion that the Klein-Gordon equation holds. Now, so far, we've already showed that the hermiticity condition holds with this ansatz. That's trivial, because that's the Hermitian conjugate of that. We also know that the equation of motion holds trivially again, because these operators are independent of space and time. The only space-time dependence is in these prefactor functions, and they are, by construction, solutions, number-valued solutions to the Klein-Gordon equation. Therefore, this linear combination, this whole thing, is automatically a solution to the Klein-Gordon equation. So we have the hermiticity condition and the equations of motion basically for free. But then we showed, and that was much more complicated to show, we showed that also the canonical commutation relations can be obeyed with this ansatz. So what we showed is that if we choose a coordinate system, x and t's, then the canonical commutation relations between the phi and the pi are obeyed if the mode functions, if those prefactor coefficient functions here, the canonical commutation relations between phi and pi are going to be obeyed if we can choose the mode functions uk in such a way that they obey this slightly horrible looking condition here. And the question arose, how do we know that there is a set of solutions uk that will do this? You see, the hermiticity condition and the equation of motion come very easily. Just choose some UKs that are solutions to the Klein-Gordon equation. You could just use one of them or 20 of them. But this is required for the canonical commutation relations. That's what makes it hard. And you can tell right away that a finite number of solutions UK are not going to be sufficient. If we write the quantum field as a linear combination of A and A dagger operators with labels k and some prefactor functions there, and it's just finitely many of them, we can never have the canonical commutation relations. The reason being that if you have only a finite number of those k, then this condition cannot hold. It cannot hold because the u are going to be smooth functions. They are solutions to the Klein-Gordon equation, which has only smooth coefficients. So the u's are smooth functions, and any finite number of terms that you add up of smooth functions and their derivatives are going to be a smooth function. But on the right-hand side, we need a Dirac delta. So clearly, we need infinitely many of those UK. However, we were able to show that we can always actually find such UKs, and we needed the condition of global hyperbolicity of the space-time to prove it, and also Darboux theorem. So we showed that there always exists a set of solutions of the Klein-Gordon equation, UK, which obey that condition here. It turned out to be a resolution of the identity in the space of solutions of the Klein-Gordon equation. That's what this really says. Now, let's move on after that. Let's ask, well, we proved that we can find a set of solutions that obeys the canonical commutation relations at a particular point in time. How again do we see that if the canonical commutation relations are obeyed at one point in time, that they are obeyed for all times? How do we know that the canonical commutation relations are conserved in time? Well, it turns out that the canonical commutation relations are kind of the Noether charges of a symmetry. The symmetry that I'm talking about is the symmetry of unitary invariance of quantum mechanics. The canonical commutation relations are conserved exactly because time evolution is unitary. And we see that here at work as well. The conservation of the canonical commutation relations is implied by the self-adjointness of the Hamiltonian, which is to say it is implied by the unitarity of the time evolution operator. The time evolution operator can be written, as always, in this way. If the Hamiltonian is constant in time, as it is in our case, but if you make the quantum field theory a little bit more complicated, you could have a time-dependent Hamiltonian, in which case you would have to have this integral here, and the time ordering operator. By the way, the time evolution in quantum theory is always unitary. So the time evolution operator that evolves the quantum system from time t0 to a time t always obeys this unitarity condition. Its adjoint is its inverse. Now, let's use that. We know, after all, that our Hamiltonian is self-adjoint. We constructed it in this way. It only has pi squares and phi squares and a few derivatives. This thing is self-adjoint. So this means that we can take, for example, the field itself at time t0 and ask, what is it going to be at a later time? And we can do that by time evolving it. And similarly, the canonically conjugate momentum field we take at the early time, and we calculate what it is at a later time by time evolving it with the time evolution operator. Right? I mean, the field is not a vector. The field is an operator in Hilbert space. That's why we have to have the U and the U dagger in this way. It's an adjoint action. But this means that the commutation relations evolve like this. The commutator of the field and its canonically conjugate momentum field at a later time is given by the commutator of the time evolved field and canonically conjugate field at an earlier time, right? So the phi at the late time t is just the u phi at the early time, u inverse, and similarly for the pi. And when you spell that out, when you spell out that commutator, then you see that it's this times that, where the u inverse eats up the u, minus this times that, where again there's a u inverse that eats up a u. And so in the intermediate multiplications, you never have a time evolution operator. You end up with time evolution operators only at the far left and at the far right. So what you find is that the commutator at the later time is given by u, commutator at the earlier time, u inverse. Which is great, because we know that this commutator is just the Dirac delta here. And so we have that it's I times Dirac delta, and then you have the u and the u inverse, and it's just that. So what we see is that the commutation relations at late time follow from the commutation relations at early time and unitary time evolution. So as I said, symmetry implies a conservation. And the unitarity of quantum mechanics implies the conservation of the canonical commutation relations. It's not usually put this way, but that's how it is. Now, in all of this, we used a coordinate system. We used the coordinate system and then said, okay, we use Darboux theorem, we do this diagonalization in terms of these blocks of 2 by 2 matrices on the diagonal, etc., etc. But there is a problem. The question arises whether the quantization that we did is coordinate system dependent or independent. Could it not be that if somebody else does this very same thing that we did, but in a different coordinate system, that they will also succeed in quantizing the theory, but they get a different theory, which somehow makes different predictions? Hopefully that's not the case. How can we check whether the quantization depends or does not depend on the choice of coordinate system? Or let's put it this way. The different kinds of coordinate systems differ in how they define what is equal time. What are the space-like hypersurfaces? And this is where we impose the canonical commutation relations. So we ask then the following. Assume that the theory is as solved as above in some choice of coordinate system, and now we change the coordinate system. For example, we take a space-like hypersurface and change it to another space-like hypersurface. We make it have a bulge out so that what is equal time is now defined slightly differently. So we used to have a set of space-like hypersurfaces, sigma, and now with the new coordinate system, we are foliating space-time, we are slicing space-time into space-like hypersurfaces that are somewhat different from the previous slicing. Different set of pancakes of space-like hypersurfaces. So we go from space-like hypersurfaces sigma to space-like hypersurfaces sigma prime. Do we get the same quantization? do we get that the canonical commutation relations hold in one coordinate system, that when they hold in one coordinate system, then they hold in all coordinate systems. That's the key thing, because it would be really bad if we quantized in one coordinate system, everything is lined up, but in a different coordinate system, the commutation relations were not fulfilled. We're not solving it in a different coordinate system. So now we want to convince ourselves that if we solve the problem in one coordinate system, we are at the same time solving it in all coordinate systems. So for that purpose, we deform the space-like hypersurfaces sigma into space-like hypersurfaces sigma prime. The proposition is that we can keep the commutation relations. The commutation relations do not depend on the particular way you slice the space-time. So here's the proof. For the proof, we start by rewriting the symplectic form FH, the antisymmetric inner product between two solutions of the Klein-Gordon equation. We write that more abstractly. Initially, we had defined it in this way. So F is a solution to the Klein-Gordon equation. H is a solution to the Klein-Gordon equation. The definition was you integrate this integrand over a space-like hypersurface. What in your coordinate system you might consider to be equal time. And the integrand is this expression here. Actually, the square root of g legally belongs as a volume component, as a measure component to the integral. And you have this expression here that you integrate over that. One thing we noticed was that it's antisymmetric. F comma h is the negative of h comma f. That was crucial, because it told us that the space of solutions to the Klein-Gordon equation has a symplectic form on it, this one. Now we want to check whether this symplectic form is robust under changing the space-like hypersurface. So for that purpose, let us rewrite this in a more convenient way. We view this here as a vector field. It is a contravariant vector field because there are two upper indices, and one of them is contracted with this lower index here. So we have a contravariant vector field. And contravariant vector fields cannot be integrated over three-dimensional manifolds. Instead, the only thing that can be integrated over 3 dimensions are 3 forms. Those of you who took my course last term will remember that P forms can be, and only P forms can be integrated over p-dimensional manifolds. So if we call this a contravariant vector field J, we will have to identify, for this all to make sense, we have to identify a 3 form, let's call it J tilde, that is really being integrated over. It's not too difficult, you see this. It's basically going to be the measure factor here. So what we have when we rewrite this expression as the integral of a 3 form over a 3-dimensional manifold is, and I'm really saying this for those who took my course last term. I mean, it's going perhaps too much into the differential geometry. It's not going to be essential for calculating cosmology or so. It's just part of a proof here. In this definition here, we defined a contravariant vector field J in this way. It's just this integrand here. And then from that contravariant vector field, we can define a 3 form. And we can do that by taking the volume form, which is a 4 form, the volume form on our space-time, and then the inner derivation takes one vector field as its argument, and it will reduce an n form to an n-1 form, so it will reduce the 4 form to a 3 form. So that whole thing is a 3 form. And that is really what is being integrated over here. Now, we need to show that the value of the symplectic form, that the value of this, doesn't change when we change the space-like hypersurface. So let's deform it. So let's say this is one choice of slicing of space-time. So here we have one space-like hypersurface. That's the sigma. But then we change coordinate system, for example, and then according to the new coordinate system, points of equal time are this way. So then, does our inner product change? Remember that the inner product is the key thing to get the canonical commutation relations. If the inner product doesn't change, if the symplectic form doesn't change, we know that everything else goes through and we solve for the correct commutation relations. So now we have these two space-like hypersurfaces here, two notions of what is equal time. And we want to integrate to get the symplectic form by integrating this way or by integrating that way. And we want to see if we get the same value for the symplectic form. So we integrate over both of them. And for that purpose, we consider this geometric construction here. Between sigma and sigma prime is enclosed a four-dimensional volume. And sigma prime can be viewed as the boundary of that four-dimensional volume here. Now we use Stokes' theorem. And Stokes' theorem says that the integral of our three-form that we just constructed over both sigma and sigma prime. So if we integrate our symplectic form both here and there and add up the two, then we get the integral over the exterior derivative of the three-form, which is the four-form, over the entire four-dimensional volume, right? Four-form has a four-dimensional integral. That is what Stokes' theorem says. And we notice that if we can show that the right-hand side is vanishing, then we're done, right? Because if we can show that the right-hand side is vanishing, then we are showing that the sum of this integral plus that integral is equal to 0. Which will tell us, I'll show you in a moment where the extra minus sign comes from, which will tell us that this integral is equal to that integral, which is what we wanted to show. So exactly how does it come about? Well, you see, if we can show that the right-hand side is vanishing, then we know by Stokes' theorem that the left-hand side is vanishing. So we know that the integral over the three-form over both space-like hypersurfaces, sigma, and the deformed space-like hypersurface, sigma prime, that thing is then vanishing, which is the integral over the sigma plus the integral over the sigma prime. But by Stokes' theorem, we always have to define an in and an out direction. And what we have is that there is an inside and an outside, and this integral here is an integral where it's always meant to be outside. So this would be, for this integral, it would be, let's say, past pointing, and for that integral, it would be future pointing. We can turn this around by redefining what we mean by that integral. So we write this integral over sigma and sigma prime in the Stokes' theorem sense. Initially like this, it's the integral over sigma prime, and you have to add the two. But both are outward pointing. And now if we turn around the sign of the first integral by saying that we make that integral, that measure, the vector that occurs here, the vector that's orthogonal to the space-like hypersurface that's involved in defining how that integral works, point inwards, which is to say future directed, then we have both integrals defined in the future directed way. And then we have that the difference between the two integrals is 0. So what we see is that the integral over sigma is the integral over sigma prime, and that is what we wanted to show. However, that is still assuming that the exterior derivative of our 3 form is vanishing. Right? We are assuming here that the right-hand side is vanishing. So our next job is to prove that dj tilde is really vanishing. Then we know that the symplectic form is independent of the slicing of space-time into space-like hypersurfaces. All right, so this is a little technical thing, but I try not to spend too much time on it. For those of you who took my course last term, this should be fairly simple things, and for the others, it shouldn't be. It's not all that important. It's just part of a technical proof. Okay, so it's not too hard. We take the 3 form, we take the exterior derivative of it. Now, the 3 form, if you remember, was obtained by taking the volume form and then taking the interior derivative in the direction, the inner derivation in the direction of our contravariant vector field J. This is also the divergence. And the divergence in the case where the volume form is induced by the metric can be written like that. In our case, we can then calculate what this is here. So this comma is just ordinary partial derivatives, and we get a lot of terms. Because what we have is a square root of g times j, and j was this contravariant vector field. Here it is. That's the contravariant vector field. Here's the square root of g. All of that stuff needs to be differentiated in the mu direction here. So we get several terms. And for example, we carry forward the g term, and then we have the term g, and we have f and d mu h. You see, let's consider the term where everything here is carried forward except for the f. The f is being differentiated in the mu direction. That gives us this term here, right? Same as that, except that the f acquired that derivative. Now, by the product rule, we should also get other terms. So, for example, this term here, where we have that the f is not differentiated, but everything else is being differentiated, right? So we write this differentiated as a term where we differentiate only f, that's this one, and a term where we differentiate everything but f. And the same treatment we do with this term here, differentiating this times that. We will get one term where the h gets differentiated. That's over here, d mu h, d mu f. And then we get also one term where everything but the h gets differentiated. Now, these two terms are the same, so I'm crossing them out. And by the way, it's usually a good trick when you do lengthy calculations. When you have two terms that cancel each other, put a label on the slash that cancels your equations, so that you can later, if let's say you have these two cancel, and so on, and you would put a slash here and a label 2, it's just faster to find a mistake if you made one, if you keep track of things this way. So I do it automatically nowadays. Okay, now this piece here, this expression, can be written as minus m squared g square root of g because of the equation of motion. That is written over here in black to remind you of how that came about. So that is nice, because then we can drop those two because they cancel, and this becomes just that expression here. And we see that it is actually, that these are twice the same term, just with a different sign, so that's really 0. Okay, so the right-hand side vanishes, and therefore, really, the symplectic form is robust against changes in the slicing of space-time into space-like hypersurfaces. So we finally proved that for globally hyperbolic space-times, and remember, these are the ones where you can put initial conditions and then calculate uniquely what the subsequent evolution will be. So we finally proved that for globally hyperbolic space-times, there always exist mode functions uk of x and t, such that our ansatz for phi and pi will succeed. It will obey the canonical commutation relations at all time, and indeed, for all possible ways that you could slice space-time into space-like hypersurfaces, you will have that the phi commute with each other and the pi commute with each other, for example. So in particular, it means, for example, this. Even if you work, let's say you work in a certain coordinate system, then you know, of course, by construction, that the phi at one time here will commute with the phi operator at another location at the same time, because at equal time, the phi and the phi commute, right? But they commute more generally whenever they're space-like separated. That's what we just proved. So not only do the phi operators commute with phi operators at the same time, phi operators commute with all phi operators that are space-like separated from them, because there is going to be an observer for whom they are equal time. Yep.
So it's, I mean, more or less just shown that J is exact or is closed, but do we have with the topology? I imagine it is also exact. Is there a meaning for the whatever operator or whatever function we're taking the series derivative
of? Very interesting. So you're saying, yeah, if it's closed and the topology is trivial, if it's contractible, then we should have that this is actually the D of a 2 form. I don't know. That's an interesting question. I think about it. Very good point. Okay, so here an example. Oh, by the way, I'm calling this equation here, this slightly terrible-looking condition on the mode functions, the condition that the mode functions have to obey such that the commutation relations are obeyed. I usually denoted that equation with a W. And the reason is that this condition here is known in the theory of partial differential equations as the Wronskian condition. Now, in the general theory of partial differential equations, they don't usually consider second quantization. The Wronskian condition is a more general phenomenon for partial differential equations. The fact that this particular thing is conserved in time is a general feature, the so-called Wronskian of a differential equation. So if you want to look up more about the background of this conservation, that's the term to go by. Now, here's an example. For Minkowski space, we should be able to go through all of these things very quickly, very easily. Here is what we get. For Minkowski space, we had found the following solution for the Klein-Gordon field. If you remember, phi hat of x and t, the complete solution to the Klein-Gordon second quantized theory is given by this expression. Raising lowering operators, the k in this case really means the 3 momentum vector. And the mode functions are given by these plane waves, which are nicely covariant up here. This is just the Hermitian conjugate of that. And the mode functions are not only plane waves, they also have this prefactor here in particular. Well, and that too. A 1 over square root of 2 omega k. So in total, the mode functions take this form. And, well, do they obey this? Better should, otherwise we made a terrible mistake somewhere. Okay, so let's verify things. Let's verify the condition W. Now, first of all, in Minkowski space, things are a little easier because, especially in Cartesian coordinates, in Minkowski space, the square root of g is 1. The g nu 0 is just the Kronecker delta, nu 0. You see, this stuff comes up in here. In the, where is it? Oh, here. Right. See, we have the square root of g, we have a g, 0, nu. Let's see how they look like in Minkowski space. Well, Minkowski space, they are simply this. And so the left-hand side of the equation W, of the Wronskian condition, is this. Square root of g and the g nu 0 is just gone now. And we have only mode function times time derivative of the mode function, complex conjugated, minus complex conjugate wave function times the time derivative of the mode function. That, when integrated over all the k variables, in this case momentum space, should give us the right-hand side of the Wronskian condition, which is I times Dirac delta. Now again, notice that we have infinitely many mode functions. Finitely many could never do it. These plane waves are very smooth. They would never add up to a Dirac delta if you only took finitely many of them. But we're integrating over infinitely many of them, so we have a chance to get a Dirac delta. This is how it all plays out. Remember, the UK in Minkowski space in Cartesian coordinates are simply given by those plane waves with a prefactor of 1 over square root of 2 omega k and 1 over square root of 2 pi to the third power. And these prefactors arise twice, once with u and one with the derivative of u star. So those square roots go away. And then we have these products of plane waves. This omega k arises from the time derivative of the plane wave with respect to time. Remember that the plane waves in the UK have this prefactor here, have this factor e to the power I omega kt. If you differentiate that with respect to t, you get an omega k down. That's how this I omega k arises. And then minus this expression here, we obtain that. And so, if we collect things together, we obtain that this is, we have some cancellations going on here. And then we have that this is given by this expression where we have that canceling. And we're just left with this integral here. You see, the time dependencies are all canceling out because they always come with opposite signs there, and only the space dependencies in the plane waves remain. But now we are just left with integrating a plane wave over all k, and that gives us a Dirac delta in x minus x prime, and that is what gives us the right-hand side of the Wronskian condition. So they do obey the right conditions. So the summary so far. To solve the quantum field theory of a free Klein-Gordon field in a curved spacetime is to solve the hermeticity condition, the equations of motion, and the canonical commutation relations. We made this solution ansatz here, where, remember, the k don't have to be momenta. In general, they are not. We showed that at least if spacetime is globally hyperbolic, then this ansatz A will succeed. There exists a bunch of solutions UK to the Klein-Gordon equation, number-valued solutions to the Klein-Gordon equation, such that the hermeticity condition, the equations of motion, and the canonical commutation relations hold. Question then is, does there exist only one such set of solutions, or could it be that there are more? Well, there are, in fact, many other such sets of solutions. And that's because the Darboux theorem, unlike the spectral theorem for self-adjoint operators, which gives us a unique diagonalization for every self-adjoint operator, the Darboux theorem doesn't give us a unique standard basis in which the symplectic form takes this special shape of being block diagonal. Darboux theorem just says there exists a basis in which it takes that form, and then you can easily convince yourself, I will convince you of that now, that there are many such bases that do the trick, infinitely many. So how do we see the non-uniqueness? How do we see that if there is, well, there always is a bunch of solutions UK that does the trick, obeys all the conditions, there's going to be many, in fact, infinitely many other bunches of solutions that do it. Well, let's see. The symplectic form for two solutions f and h in the space of solutions of the Klein-Gordon equation is given by this expression. The Darboux theorem says that there exists a basis in the set of solutions to the Klein-Gordon equation, V. So the Vn are bases in this space of solution, the vector space of solutions to the Klein-Gordon equation, such that in that basis of the Vn, the symplectic form takes this shape. And then what we did is we took that Vn basis, which was a basis in the space of real valued solutions to the Klein-Gordon equation, and then we defined from that a basis in the space of complex valued solutions to the Klein-Gordon equation. And if you remember, that's how we did it. We defined solutions Un as V of 2n plus I times V of 2n plus 1. See, that is going to be a complex valued solution because it has a real part and an imaginary part. And we showed that these Un form a basis in the complex vector space of solutions to the Klein-Gordon equation. That's how we proceeded. But Dabur didn't say that there's a unique basis Vn. And here's an example for other bases. Take any one of those boxes. See, the Dabur theorem tells us there's going to be a basis in which the symplectic form takes this box diagonal form, right? You have always this box of 2 by 2, a 2 by 2 submatrix, 2 by 2 submatrix, 2 by 2 submatrix. And let us just consider the two-dimensional vector space of one of those boxes. And let's see if we can change bases in just that two-dimensional vector space. And see if we can change bases such that the symplectic form still has that form. We can. So let's assume that V1 and V2 are the Dabur bases in that two-dimensional vector space. So assume that the symplectic form takes this shape when V1 and V2 are chosen as basis vectors in that subspace. On that subspace, the symplectic form takes that form. Then let's ask, can we change bases? Can we change bases by a linear transformation, just a general linear transformation, so that we now have a new basis of vectors V bar, and the V are a linear combination of the V bar, so that the symplectic form keeps that shape. So question is there a change of basis matrix which maps the V vectors into the V bar vectors such that after that change of basis, this symplectic form still has the old shape? So this is how a symplectic form, or just any form, will transform under a change of basis. You have the B on the right, and you have the transpose of B on the left. This is always what you get when you take a linear form and you change bases. If you're not completely sure about this, how this comes about in linear algebra, here is why. For now, just take my word for it that if you change bases, then a matrix changes in this way. Basis change matrix on the left, transposed on the right with a B. And so the question then is there a change of basis? Is there a linear transformation of the basis vector such that this product of three matrices is that? And yes, easy. So you can easily check yourself by just plugging it in. If you choose any change of basis matrix, B, with coefficients A, B, C, D, that obey that condition here, so they are of determinant 1, any such matrix will actually preserve that structure. So that means that even just within such a box, we can always change bases in many ways. In fact, it is true much more generally. You can also mix up things between the boxes and still change bases and still have a Darboux basis like that. So those Darboux bases are very far from being unique. We have riches of ambiguity in here. And unfortunately, that's not making life easier in quantum field theory, that we have all those many solutions. So let's see what that implies. What does it mean that the solution A is far from being unique? Remember, A was this. This is our ansatz. We write the quantum field as a sum of terms where we have operators that take care of the commutation relations and mode functions that take care of the equations of motion. And there was a non-trivial interplay, the Vronskin condition, that had to be obeyed. But the solution is far from being unique. What does that mean? Okay, so let's say we use several of these solutions. That means is that we can write the field, we can solve the theory either by using one bunch of such Vronskin condition obeying solutions to the Klein-Gordon equation and write down an expansion of the physical Klein-Gordon field in this way. Or somebody else might pursue the same program but may settle on a different set of mode functions, on a different set of functions. Let's call them U bar. Now that person may use different mode functions and also cook up a different name for their A dagger operators. So they will say, okay, here's my solution. That solves the Klein-Gordon equation. Leave me alone with your solution. I have my own, this one. And then somebody else comes along and says, no, I'm solving the Klein-Gordon field theory this way. Different mode functions, different A dagger operators. Who's right? Who should we believe here? Now, in Minkowski space, the case can be made that certain mode functions are to be preferred because they've been confirmed in experiments, for example, or they're the simplest and so on. But in generic curved space-time, what kind of argument can we use why we would want to use the one set of mode functions over the other? And after all, it does make a bit of a difference here. If somebody uses one set of mode functions and somebody else uses another set of mode functions, they will also have a different basis in their Fock spaces. Right? So this fellow will use these operators A to define a vector 0 that's annihilated by that, and will create then with the creation operators a whole Fock basis out of this. And that fellow will use a similar construction to come up with a Fock basis in his Hilbert space. Now, so far, actually, both would be completely in their right to do this. There's really no preference to be made. Where it becomes critical is this. If the person who did quantize this way is doing this construction, they may be tempted to say, you know what, I believe that's the vacuum state. This is the no-particle state. But somebody doing a quantization that way may say, no, I think that should be the vacuum state. But you see, this now makes a difference. This is a matter of predictions now, whether or not you find particles, if that state is the state of the theory. So basically, so far as the solution, as far as solving the quantum field theory is concerned, you can choose any one of those. It doesn't matter. Where real physics comes in, where choices have to be made is, if you want to identify what a particular vector in Hilbert space actually means. Right? So you create a Fock space here, Fock basis, and then you would like to associate the vector here with the 5k with perhaps the state that represents 5 particles of momentum k. But is it? Somebody else may have a different opinion about this. So we will have to figure out in this course how we identify what the various vectors in Hilbert space actually mean physically. Which are the states that describe 3 particles, 5 particles, and no particles. But initially, as far as the math is concerned, any one of those quantizations is completely legal. You can describe all of the physics with them. Let's go into more detail about this claim that I just made. I made the claim that, in principle, any one of those quantizations is equally good. In principle. They may not be equally convenient, but they're equally good. Convenience means, for example, you can easily say the vector 0 is the vacuum. That would be convenient if you could say that. It would be inconvenient if you have to say the vacuum vector is a complicated linear combination of things, right? It would be inconvenient. But as a matter of principle, I'm claiming that you can work with any one of those. Any one of them, and you can do all of it. You can do all of physics with any one of those representations. Let's see why I can make that claim. So here's the question. Do these solutions of the quantum field theory describe different physics? Or do they describe the same physics and they differ merely by a change of basis in the Fock space? Right? That's the alternative. Either they describe different physics or they describe the same physics, and in that case, there must be some map between the Fock spaces that shows that what you're looking at here means that in that Fock space, and that in this Fock space is that in that Fock space, right? And it's the second, it's not the former, it's the latter. In principle, it could have been that if you find different ways to solve the quantum field theory, you get different physics. But no, what we get is that we get the same physics, and the different ways of solving the quantum field theory just correspond to a change of basis in the Fock space. Not trivial, though. Now, let's be careful. I have to make some disclaimers here. There is some dependence on assumptions. It could be different physics. But here's the key assumption. Let us first assume that we can impose infrared and ultraviolet cutoffs on our quantum field theory with negligible consequences. So let's assume we have a well-behaved quantum field theory. Well-behaved in the sense that if we, instead of solving it for all of the universe, we solve it only for a really large chunk of it, it's still okay. So we assume that if we do a boxed regularization, an infrared regularization, where we have box lengths of several billion light years, then we are not really making any significant mistake in our calculations, because locally we shouldn't feel the box boundaries very far away. Secondly, let's assume that the quantum field theory is also well behaved in the sense that if you truncate it in the ultraviolet, if you neglect very, very high momenta, if you discard them, if you make it ultraviolet regular in that way, then again, you're not changing the physics at low energies, at the energies, I mean even counting the accelerator at CERN as low energy in that regard, because it's still more than a dozen orders of magnitude away from the Planck length where we would put a cutoff. So let's assume we can put an ultraviolet cutoff, so a large momentum cutoff and a small momentum cutoff, a box cutoff and a high momentum cutoff, without doing any significant damage to the predictions. And I'll talk in a moment about what the caveats could be. Let's assume we can impose those cutoffs. In that case, we are actually going to have only a finite number of harmonic oscillators in our quantum field theory. First of all, because we have an infrared cutoff, a box cutoff. Instead of momentum integrals, we will have momentum sums, momentum series, right? Because only a discrete set of wavelengths will fit into the box. So the momentum integrals become momentum series. So at that point, we have a countable infinite number of momentum modes, therefore a countable infinite number of harmonic oscillators, and therefore a countable infinite number of degrees of freedom. If we also impose an ultraviolet cutoff, so if we say no momenta larger than so-and-so, no wavelengths shorter than such and such, let's say at the Planck length or so, then it means that we are truncating those momentum series at some point, so we have only a finite number of momentum vectors. Therefore, we have a large, very large, but finite number of harmonic oscillators, a finite number of degrees of freedom. Now, when that is the case, then we can invoke a theorem by Stone and von Neumann, which says that, roughly speaking, if you have a finite number of harmonic oscillators, if you have a finite number of degrees of freedom, and you have another system, another quantum system of a finite number of degrees of freedom, they are unitarily equivalent. So assume that in a Hilbert space H, the operators xi and pj obey the canonical commutation relations. These could be mode amplitudes and canonically conjugate momentum. Amplitudes of modes of quantum fields, or just first quantization. This is a theorem of functional analysis. It doesn't care whether this is first or second quantization. It's just generally about operators. So what it says is, assume that you have a bunch of degrees of freedom, xi with the canonically conjugate momenta, pj, obeying the canonical commutation relations. Now assume also that we have in Hilbert space H tilde other operators, xi tilde and pj tilde, that also obey the canonical commutation relations. And assume there are equally many, so there are n of these degrees of freedom and n of those degrees of freedom. Now in principle, you could imagine that this might be somehow a physically inequivalent representation of an n-dimensional, of an n-degree quantum system as this. But not so. It turns out that necessarily the two systems will be unitarily equivalent. And there are two steps to see this. The first step is to realize that all Hilbert spaces that occur in quantum mechanics are unitarily equivalent. And by that I mean all Hilbert spaces that are what are called separable. In quantum mechanics, you may remember that the Hilbert space of pure states is separable in the sense that it has a countable basis. For example, you could take the basis of the harmonic oscillator. It's the Hermite functions, right? Hermite polynomial times Gaussian. They diagonalize the harmonic oscillator. There are infinitely many of them, but countably infinitely many of them. For each energy level of the harmonic oscillator, there is one. And together, they diagonalize the Hamiltonian, and being the eigenbasis of a self-adjoint operator, by the spectral theorem, they span the Hilbert space. So, the Hilbert space in quantum mechanics is having a countable basis, countable infinite basis. You may find that a little funny because we like to think in quantum mechanics also of the position eigenbasis and momentum eigenbasis, and it would seem that these are continuous, right? You can label the plane waves continuously. You can label the Dirac deltas continuously. But remember that they are not even in the Hilbert space. And truly, all the true bases of the Hilbert space, where the basis vectors are really in the Hilbert space, will be countable. And if you have any finite number of countable things, then that's also countable. So if you have like a gazillion particles, but not infinitely many, but a gazillion of them or a Brazilian of them, then their Hilbert space is also going to be countable. Then there's a theorem that says that all those Hilbert spaces are unitarily equivalent. There is only one Hilbert space of quantum mechanics. All Hilbert spaces that you can cook up one way or the other with countable sets of bases have unitary maps between them. And therefore, you can say that the math of these degrees of freedom happen on the same Hilbert space as the math of these degrees of freedom. The representations are equivalent up to, the representation spaces, the Hilbert spaces, are unitarily up to, equivalent up to a unitary transformation. That doesn't say yet that the operators are unitarily equivalent, but this is where the Stone-von Neumann theorem comes in. It says that not only are the Hilbert spaces going to be unitarily equivalent, but also there's a unitary map that relates the xi tilde operators to the x operators, and that relates the p to the p tilde operators. So you can't really cook up new physics by cooking up new representations of your computational relations. That's why I said it's unique. But there can also be pathological cases. Those pathological cases have to do with the representation theory of position momentum operators. They're unbounded operators. They can't act on the entire Hilbert space. Unbounded operators can never act on the entire Hilbert space. In order to close that loophole, one then looks at operators, at these operators, which are the exponentiated position and momentum operators. They are unitary, and as such, they can act on the entire Hilbert space, and in this way you can close that loophole. So strictly speaking, those uniqueness results are true for these operators, not for the naked X and the naked P operators. Now, I mean, it's been looked at, but these loopholes nobody has managed to make sense of them physically. I just wanted to mention that they are there. Who knows? Maybe they are important in some regard. Okay, so similarly then, what this means for raising and lowering operators is that not only are the X and the X tildes, and the P and the P tildes unitarily related, but also A and A dagger operators will be related to each other by some map. Now, there's another way out in which these different quantizations could give you different physics. And that other method by which, other occasion by which different representations, different solutions to the quantum field theory gives you different physics, could come about this way. It could be that we have a quantum field theory where we cannot impose an infrared or ultraviolet cutoff without changing the theory fundamentally.
In the Stone-Van Neumann theorem, so one of the conditions was that the representation was irreducible.
Yes, that's right.
So what does that mean?
Oh, yeah, I skipped over that. Good that you noticed that. Yeah, it means that no subspace is left invariant, right? So you could always add. I mean, for example, let's say take it as true what I told you about the X and the P and so on. They are unitarily equivalent to the X bars, X tildes and the P tildes and so on, right? So the two Hilbert spaces are the same. Now take one Hilbert space and attach to it, tensor it with another Hilbert space. It's very large and all sorts of things are going on there in principle, but your X and your P operators act as the identity on that. Okay? Then in that case, you still have that equivalence, but the Hilbert spaces are not the same, right? And so if there is, you can always tag on some extra Hilbert space to one of the pair of Hilbert spaces. You could tag on stuff on which your operators act trivially. And that could not be seen then. So you would have some extra redundancy in there that would spoil the equivalence. And only if you require irreducibility, you have exact one-to-one match. Okay, so when could it happen that we cannot truncate our quantum field theory so that we have a finite number of degrees of freedom? Remember, Stone-von Neumann requires that we have only a finite number of those degrees of freedom. A finite number of harmonic oscillators, finite number of modes, finite number of degrees of freedom. Well, for example, what could go wrong is that, if we truncate at the Planck scale, this somehow would have an effect even at low energies. We don't really like theories like that, right? So a theory where what we measure at CERN, what we measure in daily life, somehow depends directly on Planck scale physics. Might be the case, but generally we like to think that theories obey some sort of scale separation, where if you modify the theory in the far ultraviolet, it doesn't change your everyday physics predictions. If that's the case, then we have other problems to worry about. But then there is another occasion where we cannot impose a regularization, and that would be when we cannot impose an infrared regularization. That happens if we want to consider thermodynamic properties, and we are interested in phase transitions. Because in order to have the thermodynamic limit, it has to be a system of infinite size. Otherwise, we don't, strictly speaking, have phase transitions. We have approximations to them, but not the clean phase transitions with their discontinuities. So in that case, when we are considering large systems, for example, for thermodynamic reasons, in order to have a clean handle on phase transitions, then we could have that. That's not the case. And so the physics of it is that you could have different representations of your commutation relations. They would describe different physics, and they could be different phases of the same theory. So you could have a quantum field theory that has phases just like water has. You could have a quantum field theory that has a certain phase and another phase, and they would be physically inequivalent. You may wonder, how could that be understood mathematically? Now, there's a lot going on when you take things to infinity. All sorts of things can happen between finite and infinite. But one thing that definitely goes on, and is perhaps good to keep in mind when you go from finite to infinite, is this little example here in the box. Consider two vectors in a Hilbert space, A and B. And let's say that their overlap is alpha. They are normalized vectors in a Hilbert space, so the modulus of alpha is certainly smaller than 1. Because we are assuming that A is not B. So they are not orthogonal. A and B are not orthogonal, let's say, right? Okay. Now, let us consider the tensor product of finitely many of these vectors A. So it's like taking, finite many copies of the quantum system, and then we take the states to be copied too. And then we calculate the overlap with as many copies of the state B. And as long as we have a finite number of degrees of freedom, what we have is that the overlap is given by alpha to the power n, which is also still a finite number. It may be a small number. You see, as this number of subsystems or systems that you are coupling together there is increasing, you have that this number goes down exponentially, but you never have that this number becomes 0. In other words, this vector of all those A's is never orthogonal to that vector with all those B's. But in the limit where you take infinitely many degrees of freedom, infinitely many copies of these, the overlap suddenly is 0, and suddenly you have that they're orthogonal. And that can make a difference, whether vectors are orthogonal or not. And so, you see, for example, if you have two vectors A and B, then as long as they're not orthogonal, you can use the vector B to help linearly combine the direction in which A is pointing, right? You can use that as a replacement for A. You can still go in that direction, okay? But at the moment that the two are orthogonal to each other, B becomes useless for linearly combining anything in the direction of A. So it makes a sudden difference whether or not two vectors are orthogonal. And that can happen when vectors that always stay non-orthogonal, in the limit for infinitely many systems, they become suddenly orthogonal. It's just one of the weird things that can happen with infinity. And that is underlying the phenomenon that you can have inequivalent representations then. Okay, so from now on, we will take things a little easier. We will assume that an infrared and ultraviolet cutoff are possible, and that therefore the Stern-von-Neumann theorem applies. And therefore, as a conclusion, no matter which set of suitable mode functions, the UNs or the UN bars or the UN double bars or any other set of solutions to the Klein-Gordon equation that can be used to get to solve the quantum field theory, no matter which one we are using, we always obtain the same solution. We can write the phi of x and t one way, or the other way, or yet another way, and the only difference is unitaries. So if we solve our quantum field theory this way, we get a Fock basis built out of the A's. This gives us another Fock basis, gives us another Fock basis. But those Fock bases have to be just bases of the same Hilbert space. There's got to be a unitary transformation that gets us from the one Fock basis to the other Fock basis. After all, they're just Hilbert bases. They're just orthogonal bases in a Hilbert space. And if they are living in the same Hilbert space, then there's got to be a unitary map between any two bases, in particular between any two Fock bases. So for example, we could use the UK basis, define a Fock space by defining a vector 0. I'm purposely not calling it the vacuum vector, right? Because we don't know what role it plays in physics. We just define a vector that's annihilated by the A, and then build a Fock basis over that. And again, we should be agnostic about whether or not these are multiparticle states. This is just the construction of a basis in a Hilbert space on which our phi and pi and A and A dagger are acting. And so we will later have to figure out what these states mean in physical terms. For now, it's just math. So we get all these, we get this Fock basis here, or we choose another set of solutions to the Klein-Gordon equation, and we get another Fock basis in exactly the same way. Does this choice of mode functions matter? Well, as we said, in principle, it does not matter. If you choose the one Fock basis or another, they are just related by some unitary transformation. Assuming that Stone-von-Neumann holds, and we have infrared and ultraviolet cutoffs that we can do. So in particular, the phi hat of x and t can be expressed whichever way we want, in terms of the a's or the a tildes or the a dagger, a double tildes, and so on. And because everything happens in the same Hilbert space, no matter what state the system is in, no matter what pure state the quantum field might be in, let's call it psi, that state can be expressed as a linear combination of any one of the basis vectors. If our quantum field is in the state psi, we can express it as a linear combination of the Fock basis vectors of one choice or the Fock basis vector of another choice, just different bases in which we expand the same state vector. In practice, however, people are not so easy about this, and they will say, yeah, but we have an opportunity here. We better choose our mode functions cleverly so that they are convenient, a convenient choice. There's no point in choosing our mode functions arbitrarily, and then if you want to write down the vacuum state, it is some horrible linear combination of the Fock bases. It would be much more elegant if we could arrange that the vacuum state is, for example, the vector that's annihilated by the A. But then, of course, I have to know which vector in the Hilbert space is the vacuum state, so that I can then choose my mode functions appropriately, so that then the vector annihilated by the A operators is the vacuum state. So it will be a big problem that you will have to face to identify which vector in the Hilbert space is the vacuum vector. It may depend on the observer. It may depend on at what time you are looking at it. And once we've identified that, then it is convenient to choose a set of mode functions such that the corresponding A and A dagger operators are such that the A operators annihilate what we identified as the vacuum state. Okay, so so just an outlook, quick outlook to what we will get to next. It's just a brief sketch. So let's say we know the state of the quantum field, psi. Let's say it is the vacuum, at least initially. So this could be, in cosmology, the assumption that very early on, the state of the quantum field, let's say the inflaton field, the Klein-Gordon field, was in the vacuum, no inflaton particles produced, and we call that state psi. Then we choose, and let's say we know what vector that is in the Hilbert space. We can identify by some means that I'll explain. Then we choose mode functions, a set of mode functions appropriately, namely so that the A operators that come with the choice of mode functions annihilate that psi vector, so that we can conveniently say, oh, you know, with this choice of mode functions, the vacuum state is simply the state annihilated by all the A's. Now, we are going to work in the Heisenberg picture, usually. And in the Heisenberg picture, remember that the state of the quantum system doesn't change. Once it's set, it's not changing. It's only the operators that evolve in time. So by saying that the vacuum, that the state of the quantum field is psi, and psi is this zero-in vector, is the vector annihilated by the A operators coming with those un, we have identified the state that the system is going to be in forever. Now we let this quantum field evolve. For example, the universe expands. And then after a while, for example, after inflation ended, we will ask again, which vector in the Hilbert space is now describing the vacuum state? It may be a different vector now. Because after all, the operators have changed, so the eigenvectors have changed. So it could be that now it's a different vector in the Hilbert space that describes the vacuum vector. Remember, the state of the system is, of course, frozen. It was always the same Heisenberg picture. It cannot move. But it's a non-trivial question whether later on, after all this expansion, the vacuum state is still the same state in the Hilbert space. It's not. Now, a different state in the Hilbert space happens to be the vacuum state. And that's generally what we will find. And then what we can do is, we can find a second choice of mode functions for which let's call them U bar, for which the corresponding operators A bar have the property that they annihilate what is now at the later stage the actual vacuum state of the quantum field. So now you see we have two Fock bases. We have the Fock bases that came with the first choice of mode functions, and the Fock basis that comes with the second choice of mode functions. The Fock basis of the first choice of mode functions had the property that its A operator annihilated the vacuum at early times, and that is the state that our quantum field was in and will be in. And the second set of mode functions has an annihilation operator, has annihilation operators A bar, which annihilate the state that at a later stage is actually the vacuum. So clearly, the state of the system, which is frozen to be the early vacuum state, at a later time is not going to be a vacuum state. There's going to be a Bogoliubov transformation that gets us to the new Hilbert basis, to the new Fock basis. And that can then be interpreted as particle creation through the expansion of the universe. In fact, sometimes it cannot even be interpreted as particle creation because the particle picture itself may break down. The situation is so wild in cosmology that some of these harmonic oscillators can go upside down, right? So that you have that the harmonic oscillators are this way instead of that way. In which case, you cannot even interpret what happened as the production of particles, but instead you can only interpret it as an enhancement in the fluctuation amplitudes of the quantum field. But the particle picture in that case breaks down, as we will see. But still, the overall principle still holds that we identify what the vacuum state was very early on, and then we run through the evolution, and then we check what kind of state is that later on, when it's no longer the vacuum state. And it will be a state of large fluctuations of the quantum field caused by cosmic expansion. And remember that in principle it's a situation very similar to what we had for the driven harmonic oscillators. We had an in construction, a construction for in states for the harmonic oscillator, an in Fock basis, and we had an out Fock basis. And in that case, the in and out operators were simply related by the A in operator being a constant plus the A out operators. In which case we were able to tell that the ground state became a coherent state. In the case of cosmology, it's not going to be as easy as that. The in and the out operators will be related by much more non-trivial Bogoliubov transformations that will mix the A and A daggers. The A out will be a linear combination of the A in and the A in daggers. Okay, and I leave you with a little exercise here. Remember that we calculated I gave you an example for the ambiguity in the application of the Darboux theorem. You get the standard form of the symplectic form with these little 2x2 boxes on a diagonal, not only with one basis, but many bases. But I calculated through it only for one of those boxes. Okay? Now, here, more generally, remember that with respect to the Hermitian bilinear form, which is really symplectic, the mode functions obey this. No, this one is Hermitian, right? So the mode functions obey that. The complex solutions to the Klein-Gordon equation. Remember, we constructed the Darboux basis of the complex solutions of the Klein-Gordon equation, and it had this nice property that we had this orthogonality, but there's a negative sign here. And now consider an invertible change of bases in your vector space of complex valued solutions of the Klein-Gordon equation, so that we have new mode functions. So we take linear combinations of the old mode functions, the u and the u star, and the linear combinations are described by matrices A and B. That's the most general thing you can write down to linearly transform the old basis into a new basis, right? So these are the old bases, and then arbitrary coefficient matrices, and that's going to be the new basis. So with every Bogoliubov transformation, this kind of thing will happen, namely that the mode functions will be mapped into new mode functions. The A and A dagger go into new A and A daggers, that are linear combinations of the old ones, and along with that comes a linear transformation of the solutions of the Klein-Gordon equation, the coefficient functions, the mode functions. So now your exercise is to show that for the newly linearly combined complex solutions to qualify as mode functions, which is to say, for them to obey the Wronskian condition, which is to say that they obey these conditions. So for the new basis of mode functions to obey those conditions, which boil down to the Wronskian condition, those linear transformations cannot be completely arbitrary, but instead those two matrices have to obey those two conditions here. And this is useful to know when in practice you want to calculate Bogoliubov transformations. For example, for the case of the Unruh effect or black holes or cosmology. Just a bit of linear algebra, but it's good to work through that a little bit. Okay, that's it for today.